All right, so today we are making some position versus time graphs. This is kind of our first time representing motion in this way. And so there's a couple of graphing basics that we want to hit first, and that is scaling. It should not be like a super tedious process. If you get more than half of the graph used for your data points, you are good. So looking at this first problem here, we have Albert who lives 1,000 meters away from school. He is going to walk 1,000 meters total. On our graph, we see that there's 4 like big boxes here, so we want to maximize that space. This is going to be pretty easy to scale: 250, 500, 750, and 1,000. Okay, so that was easy for position. For time, right, reading the problem, he's going to walk for 5 minutes. He stops to talk to a friend for a minute, so that's 6 minutes. And then he's going to travel for 9 more minutes, so that's 15 minutes total. Okay, so 1, 2, 3, 4, 5, 6. I have 6 big boxes and 15 minutes to allot. So instead of thinking about 6 boxes, why don't I think of it as like 3 like jumbo boxes? So I can do 5, 10, and 15 here for my scaling. Okay. At the beginning, he is at his house, and it says to put his house at the origin. So he's going to start here. Okay. After walking for 5 minutes, he has reached 500 meters away. Now, we're going to make an assumption here. We're going to assume that Albert walks at a constant speed or a constant velocity. So he's not going to be like gradually speeding up or slowing down. He's just walking. Okay. If that's the case, then we know that since velocity is the slope of a position versus time graph, we are going to connect these two dots with a line segment. Okay. So since this is like a story, it's not raw data that we collect in the lab. We are able to like make this kind of sketch with a line, all right, to represent Albert's motion over the first 5 minutes. Okay. After he walks for 5 minutes, he stops to talk to a friend for a minute. So he has stopped. If I ask you, hey, where is Albert right now at the 5.5 minute mark? Well, Albert's not going to teleport or anything. He should still be there. Okay. And so he's there for a whole minute. So that's going to be a horizontal line segment, like so. Okay. After that minute, Albert is going to then walk the remaining 500 meters over the course of the next 9 minutes. So that means 15 minutes after he starts walking, he's going to be at the 1,000 meter mark. And once again, we will assume that he is walking at a constant rate. So it's not going to be a curve, it's going to be a line. Okay, that takes us from 500 to 1,000. Okay. For your convenience later on, we're going to go ahead and label these ordered pairs. Yes, order these labeled pairs. So this one is obviously 0, 0. This first point is going to be 5, 500. All right, this next point is going to be 6, 500. And then this last one is going to be 15, 1,000. Okay. For the next graph, you can use the exact same position and time scaling as we did on this first graph. For graph number 3, pick something reasonable, it should be good. And then for graph number 4, on the horizontal part of the graph, going by 5s and 10s and 15 will work there. So go ahead and take a few minutes, and with your table group, complete those 3 graphs, and then in a couple minutes we will discuss the questions that go along with it. All right, we're back. Hopefully you've done those other 3 graphs. Let's talk about these questions that are attached. So as we're looking at Albert's graph, you can see that these questions are focusing on the difference between instantaneous velocity and average velocity. we hopefully already know that velocity is related to the slope of the position versus time graph. But, well, what slope are we looking at, right? So at time equals 4 minutes, that is like a single isolated point. That is going to be like right here. Okay, so since these position versus time graphs, they are a collection of line segments, we're going to be looking for the slope of this line segment. Okay, so we could just choose like the starting point and the ending point here, and we can run just like your basic rise over run calculation for that. So since velocity is our displacement over time, right? We're looking at Albert's most recent position minus Albert's starting position over final time minus initial time. So he ends up, for this line segment, he ends up at 500 meters away. His starting position was 0, and the time that it took was 5 minutes, and we looked from the beginning. Okay, so this is how you would find the slope of this particular line segment. And so 500 divided by 5 is 100 meters per minute. Okay, technically, since it's velocity, we want to indicate a direction as well. He's going to school, so we can just say towards the school. Okay, it also asks us to explain how you can determine this graphically. This is just going to be like a reminder for you later, right? As you're trying to find the instantaneous velocity of not necessarily just lines, but also curves. So for this, right, since we had constant velocity, it was easy, right? We just looked at the slope of that particular line segment. Okay. As we get to non-constant velocity motion, if we had a position graph that was like a curve, so for example, if we had something like this, right, so maybe something that looks like a parabola, if we wanted to find the instantaneous velocity at some arbitrary point along this function, we would need to approximate what's known as a tangent line. A tangent line intersects your function at just one point, not two, not three, just one. And so your tangent line, kind of as you like move this protractor around, you can see that it becomes like more and more vertical, right, as I scoot it along that parabola. Technically, how to do this, you would need calculus. We can make some pretty good approximations of tangent lines. But the official way to determine it graphically is through the use of a tangent line. Right? But that's kind of a topic for later. For now, if we're looking at line segmented position versus time graphs, you're just looking for the line segment there. Okay? Question number 2 is asking us about average velocity. So you can see with average velocity, it gives us a specific time range to look at, from time equals 2 to time equals 15. We can't just average the velocity. Graphically, this is actually pretty significant. So let's actually take a look at what's going on there. So at time equals 2, so time equals 1, time equals 2. So this ordered pair right here, right, we can also confirm based on the number that we calculated here. Albert is traveling at 100 meters per minute during the first 4 seconds, so that means at time equals 1, he should be at 100. At time equals 2, he should be at 200. So this ordered pair is 2, 200. So from time equals 2 to time equals 15, well, remember what our definition of velocity is. It is the change in displacement over the change in time. So I can essentially just take these 2 ordered pairs and plug them into our velocity formula. Right? So at the end, Albert ended up 1,000 meters away from his house. At time equals 2, he was 200 meters away from his house. and then we would do 15 minus 2. Which is a pretty ugly fraction. Let me crunch that real quick. Oh, look, I've got it there. 61.54. Meters per minute towards school. Okay. There are kind of 3 different velocities that Albert has from time equals 2 until time equals 15, right? Because he's traveling at 100 meters per minute here. All right, he's traveling at 0 meters per minute here, right? Because he's stopping to talk to his friend. And then here, he's going slower than 100 meters per minute, but definitely faster than 0 meters per minute. When you crunch all those numbers together, the average of those 3 numbers is not 61.54. That seems like a lot of work. You'd have to do a weighted average with respect to time to actually get like the correct answer. So it's a lot of work. It's much easier just to look at your starting point and your ending point. That's what's really nice about displacement. What's really nice about velocity is that it doesn't matter what happens in the middle, right? Only your starting and ending points are going to be used in a calculation. Okay. When we did this calculation, essentially what we did is we used the slope formula with this point and this point as our ordered pairs. And so when we found the slope, we found the slope of an imaginary line running through these 2 points. And so for our instantaneous velocity, that was a tangent line. It intersected at just 1 point. For this one, right, the name of this line that intersects our function at 2 points is called the secant line. And we use secant lines to determine the average velocity. Okay? Instantaneous velocity is just like the line that is parallel at a single point on a function. Your secant line passes through 2 points on the function, so those 2 slopes mean 2 different things. That's all I have to say about average and instantaneous. Okay, for graph 2, here we've got a throwback, Bennifer and Brangelina. I think that's Ben Affleck and Jennifer Aniston and Brad Pitt and Angelina Jolie. I don't know, it was a long time ago. So question number 1 over here, what's Brangelina's instantaneous velocity at 2 minutes? We're looking for an instantaneous velocity. Oh, how convenient. At time equals 2, oh, I don't know exactly what that ordered pair is, but I know that I'm looking for the slope of this line segment. And so that's just going to be 500 minus 0 over 10 minus 0, which is 50 meters per minute. And they are going home. Oh, I guess I could have showed you the graph since I didn't actually show y'all earlier. Okay. So, our next question says, if Brangelina had maintained this velocity for the entire trip, how long would it have taken to travel the entire distance? So, there's a couple of ways that we could do that. Let's look at the equation way first. So when we're solving physics problems, we like to collect all of our information together, right? I want to list my givens and my unknowns. So I know that the velocity that I'm trying to maintain is 50 meters per minute. Okay? I want to know how long it will take. So I want to know what the duration of this hypothetical new trip would be. And then the entire distance from school to Brangelina's house is 700. So based on the information that's given, I know that the formula for velocity is delta x over delta t. I can rearrange that, multiplying both sides by delta t. So I'd have v times delta t is equal to delta x. Let me rearrange it one more time to solve for my time. Is going to be equal to delta x divided by the velocity. Okay, so then plugging in my numbers, I need to travel 700 meters at 50 meters per minute. And my units do work out, right? The meters cancel out. The minutes is going to pop from the bottom to the top. So my answer is going to be in minutes. 700 divided by 50 is 14. I didn't actually do it in my head. It's because I remembered it from earlier. So 14 minutes. Okay? Graphically, there's a pretty easy way to do this. Now, I don't know how well your copy's printed out, but mine's pretty good. Okay? If Brangelina is going to maintain this same velocity, well, since the velocity of a position versus time graph is represented by the slope, essentially we could figure this out by just continuing the same slope for 700 meters. Okay, so if I were to continue this line until, right, we get to the vertical axis value of 700, well, that's going to be right here, and looking carefully at what we got here, yeah, right, confirmed. That is going to be 14 minutes of travel in order to get to 700 meters away from school, aka Brangelina's house. Okay. Moving on to graph number 3. So you graphed both Zach and Xander's data on the same graph. Okay. I actually don't have a whole lot to say about graph number 3 because we can kind of work this backwards with our questions. Okay. How do these average velocities relate to the result of the race? So let's talk about the result of the race. Xander and Zach arrive at their final destination at the same time. So they are in the same spot, same ending spot at the same time, which means they tied. Okay, that's kind of a trick question. The result of the race, there was no winner, there was no loser. They ended up at the same place at the same time. So hold up. If they tied, then they have the same displacement over the same time interval. So they are the same. Sorry, give me one moment. Okay, I think we're back. I hope we're back. I just had to close my door for a moment there. So if you wanted to calculate what that average velocity is, y'all are capable of plugging those numbers into your calculator. They traveled 20 miles in 23 minutes. So crunch that. That's going to be your answer. All right, the last graph, my favorite. I really identify with Freddie because I feel like I have to turn around and go back to my house and pick up whatever I forgot more often than the average person. So Forgetful Freddie, he has to backtrack, right? So that's what's going on in this section here, right? He has to turn around, he has to return back to the origin, which is his house, and then he has to run to school. So now we're looking at the difference between average velocity and average speed. So velocity is nice because it involves displacement, and displacement, the only thing that matters is your starting point and your ending point. So the average velocity, displacement over time, well, Freddie's school is 1,500 meters away from his house. His whole entire journey today took him 15 minutes. And so his velocity, 1,500 divided by 15, is 100 meters per minute as we go towards school. Okay, it's not bad. Freddie's average speed, though. The formula for speed is total distance over total time. And remember that distance is a scalar quantity, so it's cumulative, right? You can only ever gain more and more steps, right? You can't like walk backwards and take back the distance that you walked. Like you already spent the energy moving your leg, right? So distance is only ever going to accumulate. So in this first part, right, he walks 750 meters. Okay? In the second part, if we are looking at distance, he's going to walk another 750 meters. And then in the last stage, one big chunk, he travels all 1,500 meters in just one big step. Okay? So our total distance then, 750 plus 750 plus 1,500, all right, divided by the total time of 15 minutes. That's going to be 3,000 divided by 15, which is 200 meters per minute. So his average speed is twice his average velocity. Okay, so it's all that vector stuff versus the scalar stuff. Since your velocity only depends on your start and your end, right? We don't really care that Freddie had to like turn around and go back, right? But Freddie's legs will definitely care that he had to run all the way back and then run to school. So his average speed is much higher than his average velocity, just like how your distance traveled is always greater than or equal to your displacement.